Hey everybody, it is time for lab number 6. Lab number 6 is another lab where we're looking at connective tissues. In lab number 5, we looked at connective tissue proper, we looked at areolar tissue, adipose tissue, dense regular, and dense irregular. Today, we're moving on to look at what's called supporting connective tissues. And supporting connective tissues, there's two varieties, and we're going to look at both of them today. Two varieties we're going to look at are bone and cartilage. And we are starting out with cartilage. This is cartilage that we're looking at on the screen right here. This is cartilage. Now, in fact, there are 3 kinds of cartilage. There is a kind of cartilage called elastic cartilage, which, as you can probably guess, you can stretch it and it can snap back. You find that cartilage in your ear, for example. Think about how bendy your ear is. There's another kind of cartilage called fibro cartilage, which is really strong. And you actually have that in your intervertebral discs, the pads that separate your individual vertebrae in your vertebral column. Now, you should know these two guys exist, but we're not going to look at them right now, okay? Instead, we are looking at a kind of cartilage called hyaline cartilage. The word hyaline means glassy, so somebody thought this cartilage looked kind of glassy, and it kind of does, not microscopically, but if you look at the gross anatomy of it, it kind of looks kind of shiny. So I can see where they're coming from with this. Now, we find this hyaline cartilage in our respiratory tract. So if you actually take a second and take your fingers and find your trachea, the rings that you feel in your trachea are made out of hyaline cartilage. If you think about your ribs go for a while from your back, from your vertebral column, your ribs wrap around, then eventually they have a piece of cartilage that joins them to the sternum. So if you find your sternum and you go a little bit out, you're feeling the cartilage that's connected to the ribs. Now, you also find this type of cartilage on your bones at your movable joints. So if you think about where your humerus in your arm meets your scapula to form your shoulder joint, there's hyaline cartilage right there. And the reason we have this cartilage at all of these places is because it is perfect for them. It is strong, it is firm, but it has some give to it. It has some flexibility. So think about taking a big deep breath in, the expansion of your chest. You need that flexibility of that cartilage right there. You need the flexibility, but you also want the strength. And hyaline cartilage does a good job of being firm, being strong, but also being flexible. Now, let's talk a little bit more about what we see here, okay? So, hyaline cartilage, it is right here, all right? It is a connective tissue. It is a typical connective tissue. So it is mostly made up of ECM. Do you remember what ECM stands for? Extracellular matrix. And this is the matrix right here. This purplish, pinkish, lavenderish stuff is the matrix. There are 2 important things in the matrix as far as you and I are concerned. Collagen and water. Collagen is going to give it tensile strength. We know that collagen does that already. The water is what gives it a little bit of squishiness and flexibility. Squishability and flexibility. Now, I do see cells here as well. All of these nuclei belong to cells, and these cells are known as chondrocytes. Chondro means cartilage. So these are literally cartilage cells. Now, when I see a chondrocyte, that chondrocyte wasn't always a chondrocyte. It used to be something else. It used to be a cell called a chondroblast. So chondrocytes were once upon a time these cells known as chondroblasts. So this guy right here, he's currently a chondrocyte. He used to be a chondroblast. Chondrocytes are kind of like the retired version. They're just hanging out and not doing much, okay? Chondroblasts are the active youngsters. The chondroblasts make the matrix, and then once the matrix surrounds the cell, the chondroblast quiets down and becomes a chondrocyte. And we actually name the little space in which we find the chondrocytes hanging out. Each of these spaces is called a lacuna. Many are lacunae. One is a lacuna. All right. So when we look at this, we got to know Haeline cartilage right when we see it. We got to know it's in your trachea, your rib cage, at movable joints. We got to be able to recognize that this is the matrix, all this purplishness. Collagen for tensile strength, water for squishiness and flexibility. We got to be able to recognize these cells, the purple guys here. They are chondrocytes. They used to be chondroblasts, which made the matrix. Now the space, the whiteness, where the chondrocytes are sitting, each of those spaces is called a lacuna. All right. And with that, we can move on. I got another Haeline cartilage picture for you here. Find these three things and then keep on going. And as we keep on going, we're done with cartilage. Yay. We got one more thing to look at today, and it is bone. However, bone is a doozy. There is a lot going on when we look at bone tissue. Now, what I've got over here, right here, this is what's called a long bone, okay? This is a long bone. A long bone is basically a bone that is much longer than it is wide. So all your finger bones are long bones. If you bend your fingers, you can see all three finger bones on your four fingers and two finger bones on your thumb. Your metacarpals in your hands, so if you find your hand bones, those are long bones. Your radius and ulna in your forearm, your humerus in your upper arm, your femur, your tibia, your fibula, your metatarsals, and your long bones, and your toe bones. Those are all long bones. Okay? They're all long bones. Now, the long bone has a shaft and two expanded edges. So as I look at this long bone, I see the shaft right here, and I see a expanded end right there. And we'll cover this more in lecture. I'm just going to give it to you now. The expanded end of a long bone where you make a joint is called an epiphysis. The shaft of a long bone is called a diaphysis. So the shaft is called a diaphysis. The expanded end where you form a joint is called the epiphysis. Okay, so we're doing a little bit of bone anatomy here, all right? Now notice that in the diaphysis, in the shaft, there is this cavity that is called a marrow cavity. So in the shaft is a marrow cavity right there. And you can guess what's in there, right? In a marrow cavity. Man, that's not good handwriting. Trust me, that says marrow cavity. In the marrow cavity, we are going to find bone marrow. We'll talk more about bone marrow later, okay? What I'm really interested today is this bone in the diaphysis, in this shaft. This bone surrounding the marrow cavity in the shaft, the diaphysis. That's what I'm super interested in today. And what we're doing here is we're cutting out a piece of pie, piece of bone pie here, cutting out a wedge. And this is a wedge of bone from the shaft, the diaphysis of a long bone. All right, this is known as compact bone right here. It's compact because when you look at it with your naked eyeballs, it does not look like it has any holes. When you look at it up close, like we're doing now, it's got holes. But not when you're looking at it just with your naked eye. Compact bone is going to be on the outside of all your bones, and it makes up this shaft. Now, what I want you to notice here is just how many cylinders of bone there are in this tissue. There are so many bony cylinders. Like I got just rings around each other here. Rings here, rings here. Now, why do you want to do this? Why do you want to have cylinders of bone? Well, let's think about that for a second. This guy right here is the femur. If I had to ask you, give me a big job of the femur, what might you say? You might say, big job of the femur is to be involved in movement of the lower limbs. That's okay, yeah, not bad. What's another job, though? Another big job of the femur? Well, the other big job of the femur is to support your weight. Now, cylinders are really good at doing that. I wonder if you took a piece of paper, and I'm actually doing this right now, and you roll a piece of paper into a cylinder. Not even a tight cylinder, just like a nice cylinder. And then you put a piece of tape on it so it stays put. So let's say you made a cylinder. Can I make a cylinder right here? I can kind of make a cylinder. I can sort of make a cylinder, right? Put another one down here. Kind of make, that's not what I want to do. Trying to make a cylinder here. Let's make a cylinder. So let's say you made a cylinder like this. Okay? You took a piece of paper, you rolled it up, and you put a little strip of a little piece of Scotch tape on it right here. And then you stood it up. Pretend that this cylinder is standing up. I have mine standing up on my desk right now. What I'm about to do, I took a single piece of paper and I made a cylinder. I'm going to put my phone on it. Totally supports the weight of my phone. Absolutely supports the weight of my phone. I have a coffee cup here. Don't worry, it's empty. I'm going to put the coffee cup on top of my phone. I swear to God, I'm doing this right now. I wish I had a camera going. That would make things so much better, okay? So I have a single sheet of paper rolled into a cylinder, and I put my phone on it, and on top of my phone I put a coffee mug, like a ceramic coffee mug. And the paper supports it fine, totally fine. I just stuck a pen in the coffee mug. I just put my mouse up. It wants to move a little. I just put my mouse in the coffee mug too. That's kind of gross, actually. Why did I put my mouse in a coffee mug? Let's take that out. I got a stapler here. I'm going to put a stapler in there too. That's better. There we go. It is supporting it beautifully. So the point I'm trying to make here, and I'm just, you heard the crash, right? When I took stuff down. The point I'm trying to make here, I'm not just trying to have fun, although I am. The point I'm trying to make here is that cylinders are super strong. Cylinders are really, really strong. Okay? Some quick extra credit project for me. Make me a single piece of paper cylinder, put something heavy on it, take a picture of it, send it to me. Brand new extra credit project. Spur of the moment extra credit. It's my favorite kind. And you get my admiration. The heavier the thing you put on the piece of paper, the better. So use a single piece of paper, piece of tape, make a cylinder, put something heavy on it, see if it stays. Take a pic, send it to me, extra credit. All right, cylinders support weight, okay? And there are so many cylinders here. Let's keep going. We're actually gonna name some of these cylinders and these parts. We're going to kind of see how they work. So, like we said, we got lots of cylinders, all right? I put a red circle around a whole bunch of concentric cylinders, concentric rings. Do you know that word concentric? That's a good word. Concentric refers to things that are sharing the same center. So each one of these rings of bone tissue, each one of the rings has the same center right there, okay? So those are concentric rings of bone tissue. And this collection of concentric rings of bone tissue is called an osteon. So my red circle is on what's called an osteon. And this is what's really making up this bone tissue. Remember, I'm in the shaft of my long bone here. The shafts of our long bones are made up of osteons. Now, there's a bunch of osteons here. I got the one that I circled in red. This is one, they just kind of expanded the cylinders, made each one a little higher than the next. This is an osteon right here. This is another one over here. I got another one where the green and blue arrow are. I got another one. Some of them are kind of like squished together. Another one, chunk of one. So I have a lot of osteons. A lot of osteons means a lot of cylinders of bone tissue. A lot of cylinders of bone tissue means a lot of strength. So an osteon is a very important structure. It is what the compact bone is composed of. As we look at these long bones, as we look at these weight-supporting shafts. Now, within my single osteon, each of these rings of bone matrix, that's what they are really, rings of bone matrix, is known as a concentric, again, because they share the same center, lamella. Lamella basically just means layer. So each of these rings is a concentric lamella. So over here I put a blue arrow on one. This is one concentric lamella, another concentric lamella, concentric lamella, concentric lamella, a whole bunch right here. And they are rings of bone matrix. They're cylindrical rings of bone matrix. They're concentric because they're sharing the same center. The center would be this hole right here. You can find a bunch of versions of these guys in all these osteons. Each of these guys is called a central canal. So the concentric lamellae are going to surround the central canal. Now, like I mentioned a moment ago, the concentric lamellae are rings. They're cylinders of bone matrix. As bone matrix, they are made up of two primary things. They're made of good old collagen. Again, we have collagen to resist tension, but they're also made of calcium phosphate. And that's what makes the bone hard, the calcium phosphate. If you are a chemistry nerd like myself, then calcium phosphate right there. Calcium phosphate makes the bone hard, which lets it resist compression. That's what weight support is all about. It's all about resisting compression. Now, the central canals, all the central canals, they are going to be passageways for blood vessels and nerves. Bone is a dynamic, hungry tissue. Bone is very dynamic. Bone is very in need of nutrients. Bone has arteries, veins. Bone has nerves that convey information. When we looked at cartilage a moment ago, I didn't mention this, but cartilage is basically avascular. It's basically avascular, yeah. Tendons, ligaments, basically avascular. Bone is quite vascular. This is why oftentimes it's easier for a bone to heal than for cartilage, tendons, and ligaments, especially as you get older and older. Good advice I'm going to give you right here. Good life advice. If you're going to break a bone, if you're going to tear a ligament, tear some cartilage, do it while you're young. Don't be my age and breaking a bone. It's no fun. All right. What else we got? We got some other stuff going on here, okay? One of the challenges in having cylinders. So let me draw a cylinder here. Let me draw a circle. I'll just draw a circle. Boom. Draw 3 circles. Dun, 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 dun. Circle number 2. Circle number 3. I'll do 4. Going crazy here. I drew 4 circles. When I try and pack cylinders or circles together, I am going to have leftover space. Colored in the leftover space in blue right there. I can see there's an area between osteons right here, for example. There's an area between osteons right here. These areas between osteons, well, we can't just leave them empty. That wouldn't be good strength-wise. So what we do is we fill them with little layers of matrix. I mean, check it out. You can see little layers of matrix in there. I'm going to click on a couple here. Boom, boom, boom. Little layers of matrix in the regions between the osteons. Those little layers of matrix, since they're between the osteons, they are called interstitial lamellae. The black arrow is pointing at one of them. Interstitial, in between, is the idea we get from the word interstitial. So in between the in between the osteons, we have interstitial lamellae. All right. We also encounter a problem on the outside. Let's say this was the outside of the bone up here where I drew my pink circles. We would have this like space here, right? This space right here, we have these bumps. So what we do is we wrap the whole bone itself, we wrap all the osteons in these big rings of matrix. So if you look out to the right here, I have all these big rings of matrix that are surrounding all the osteons. These big rings of matrix, they are called circumferential lamellae. You guys know your geometry, you know the circumference of a circle, distance around it, right? So these lamellae go around the circular shaft. Thus, they're called circumferential lamellae. I'll also have some circumferential lamellae not quite as big as the ones on the outside. I'll have some on the inside as well. All right. Awesome. And we are done this slide. We did a lot here. Oh, we're done that slide. We're not quite done this picture. There's something else we got to point out. I mentioned a moment ago to you that the concentric lamellae were made of bone matrix. They're rings of matrix. The interstitial lamellae and circumferential lamellae are also bone matrix. Well, if there's bone matrix, there has to be bone cells. Okay? And there are bone cells. These bluish guys here, blue arrow on one, they are bone cells. They are osteocytes. Whoops, didn't have my drawing tool going. They're osteocytes. So the blue arrow is on an osteocyte. Osteocyte, literally bone cell. Osteocytes are found in spaces between the lamellae. These spaces are known as lacunae. So some of the lacunae pictured here are empty. All the ones I'm clicking on right now, the one with the red arrow upon it. These are empty lacunae. Lacunae house osteocytes. Osteocytes, once upon a time, were cells called osteoblasts. And osteoblasts make the bone matrix. So chondroblasts make cartilage matrix. Osteoblasts make bone matrix. Fibroblasts make the fibers of the matrix of other connective tissues. So osteoblasts make matrix. When they're surrounded by matrix, they turn into osteocytes. And they're hanging out in lacunae. Now, when we did cartilage, I told you the chondrocytes were retired. Not so right here. The osteocytes are not retired. They're still active cells. They are monitoring what's going on in the bone. I mentioned earlier, bone is a dynamic tissue. Bone is a dynamic tissue. So when you lift weights, if you lift weights, if you don't lift weights, you should start lifting weights. Good for you. When you lift weights, you stress bone. That stress on the bone is measured by osteocytes. Then osteocytes will communicate with other bone cells, including osteoblasts, and tell them, hey, you need to make more bone here and make more bone there. And other cells, you need to take bone away here and here. And we remodel our bone and we make it stronger and stronger. And osteocytes are vital to that process. Building strong bones, super important, especially if you will undergo menopause someday. Humans who undergo menopause, they are going to deal with a demineralization of their bones, a weakening of the bones. And the stronger we can get those bones before menopause, the better we're going to be. So, yeah. Sorry for my digression. Let's keep going. Let's keep flying. I don't know if we're flying, but we're moving. We're doing stuff. All right, so remember, this is a wedge of compact bone tissue. It is from the shaft of a long bone, right? If I jump back, looking at that wedge right there, from the shaft of the long bone. Look how my wedge includes the outside. So the outside of the bone is here, and the inside. The inside of the bone would be here. And the inside of my wedge, the inside of my compact bone here, is lined by a membrane called the endosteum. It's kind of like endosteum, then they took out one of the O's. It's it's inside the bone. A little thin connective tissue layer. Outside, you have a thicker connective tissue layer. It's actually dense irregular out here. Remember dense irregular from last lab? This is called the periosteum, this outer membrane. And the periosteum has got to be dense irregular because it needs strength. It needs strength because ligaments and tendons attach to it and pull on it, and you better be strong. But wait a minute, if ligaments and tendons are pulling on this membrane, the membrane has to be pulling on the bone. So there has to be a really strong set of attachments linking this membrane, periosteum, to the bone here. And we actually see it. We see these bundles of collagen right here, these whitish things, pink arrows are on them. These bundles of collagen here are called perforating fibers, and they link the periosteum to the bone. So do me a favor, find your biceps muscle in your arm. Straighten your elbow and then contract that bicep muscle and make your elbow bend. Now when you contracted that biceps muscle, that muscle pulled on the tendon. You can actually feel these tendons in your antecubital fossa, in the pit of your elbow, where you would get blood drawn. You can get blood pressure measurement taken right there. You can feel the tendons there. So the muscle pulls on the tendon pulls on the periosteum pulls on the perforating fibers, and the perforating fibers pull on the bone itself. Awesome. Now, hey, by the way, this periosteum is called the periosteum. Peri means around, right? Perimeter means around, right? We met pericardium not too long ago. That meant around the heart. Periosteum, around the bone. Okay. Now we just turn the same model around. I'd rotate it so I could show you the periosteum on the outside. You can still see my perforating fibers going into my circumferential lamellae right there. I can also see the endosteum lining the interior. Now the interior is actually what I'm seeing here is some spongy bone. That's why there's all these holes in it. So the endosteum is lining a region of spongy bone. Spongy bone is different from compact because it's got visible holes like a sponge. And I'm going to find spongy bone within my marrow cavity like this and in other places too. Okay. Excellent. I rotated the model again so I could show you the long view of a central canal right here. This is a central canal. Remember, blood vessels and nerves will be running in this central canal. You should be able to see the concentric lamellae here. So I'm going to put some, let me switch to red. Red's better than gray. Got some concentric lamellae here. Kind of look up top, you can see them in their sort of more ring shape up here, right? I can also see a bunch of lacunae. There's a lacuna right there. There's a lacuna right there. Now these are empty ones. In reality, they would have osteocytes within them. All right. Let's keep on moving. So, again, I'm on basically the same view, but I'm showing you something new here. This is a central canal over here. Central canal right here. I'm going to put a C and another C in my central canal. Blood vessels and nerves run vertically through central canals. But you know what? I got some horizontal stuff as well, right? I got a horizontal passageway right here. This is a passageway for blood vessels and nerves to get in and out of the bone and to connect between central canals. This is known as a perforating canal. So while central canals go along the long axis of the bone, perforating canals run transversely through the shaft of the bone, carrying blood vessels and nerves. All right, let's see if we can switch models. Yes, we did. This is a model of one osteon, all right? Right here, I got a big vein. The blue guy's a big vein. There's an artery. I got a pair of nerves. I got a lymphatic vessel down here. All these rings here with the 5s on them, those are concentric lamellae. See some interstitial lamellae up next to this osteon. This whole thing is an osteon, right? I'm going to basically circle this whole guy here, like so. This whole thing, I messed up a little bit right there, but you get the idea. This whole thing is an osteon. Central canal with blood vessels. Concentric lamellae right here. This is a lacuna, another lacuna, another lacuna, another lacuna. Some of my lacunae are shown with osteocytes in them. So this is an osteocyte right here. I got what? 1, 2, 3, 4, like 5, 6, maybe like 6.5 osteocytes here. Remember, osteocytes were once osteoblasts. They become surrounded by matrix and they turn into osteocytes. But remember this also. Osteocytes are not retired like chondrocytes. Osteocytes are still active cells. They're monitoring bone tissue. They're signaling other cells saying, hey, build bone here, break bone here. And so osteocytes are hungry. They need nutrients. They generate waste. They need oxygen. They generate CO2. They need a way to pass information to each other and to other cells. And what you'll see, if you look at just one of these empty lacunae, like let's look at this empty lacuna right here. Okay, let's put a yellow dot in it. And let's look at this empty lacuna right here. You can actually see there are these very tiny channels that are connecting the lacunae. These tiny channels, someone thought they were tiny canals, so they are called canaliculi. And then the osteocyte is actually like a spider with all of these legs sticking out. It's part of the cell itself. Got to draw 8 because it's a spider, right? It's a spider with 8 arms, 8 legs sticking out. And what happens is, let's say we got one osteocyte right there. Whoops. Make me another osteocyte right here. 1, 2, 3, 4, 5, 6, 7, 8. The arms and legs of neighboring osteocytes touch one another. And at that point right there, at that junction right there, at that junction, let's make it a black arrow so I don't get confused. At that junction, there are gap junctions right there, allowing the cells to exchange nutrients, information, wastes, whatever need be. So, even though the osteocytes are encased by bone, they have these little passageways that they use, that they send extensions of themselves through so they can talk to one another. It's really pretty cool. All right. Here is another pair of views of the Osteon model. So I just showed you the top view of this model. Now I'm showing you lateral views. So can you look at this and find me some osteocytes, some lacunae, some canaliculi, some concentric lamellae, some interstitial lamellae, and a central canal? Find all that stuff for me. And now, folks, we are done with models. We are just going to look at some microscopic tissue. So this is actually real bone under the microscope. I'll walk through this with you here, okay? I'm not going to make you do this on your own very first time. But I'm going to ask you, can you see a central canal? I'm going to start with the last one here. Can you see a bunch of central canals? I see a lot of central canals. I just put a green arrow on one right there. That is a central canal. Here's another one. Another one. Another one. These are all central canals. Now, if I found a central canal, well, what's a central canal at the center of? The central canal is at the center of an osteon. So I'm going to throw a circle around an osteon here. There is an osteon. Now, if I look in this osteon, it kind of looks like it has the rings like a tree, right? You ever look at a tree that's been cut and you see the rings? And all these rings here, they're very skinny. All these rings here are concentric lamellae, which means that any rings over here, for example, any rings in this yellow blob that I just drew, those would be interstitial lamellae. All right, what about lacunae? Can you see any lacunae? I see a lot of lacunae. Let's look at the upper right-hand side. There is a single beautiful lacuna right there. Now, in this microscopic view, they've actually washed away all the cells. So it's just a mineral part that's left over. So these lacunae are empty. Of course, they would have osteocytes within them if it was real living tissue, or if the bone slide had been prepared differently. All right, awesome. Let's keep going. Zooming in on a single one right now. I'm going to make you do this one on your own. Do you see the osteon, concentric lamellae, lacunae, and the canaliculi? Make sure you can notice all of those things. If you get stuck, shoot me an email. Okay, this is actually a really beautiful slice here. They've cut this so that we actually see the perforating canal between two central canals. So we can see that passageway that allows blood vessels and nerves to travel from one central canal to another. All right. Whoops, went too fast there. And last but not least, we changed to a different kind of microscope here, an electron microscope, so we can see just how crazy the osteocytes are. I mean, when I drew my osteocyte spiders earlier, I gave them 8 legs. But look at this dude here. He does not just have 8 legs. Look how many extensions come off of him. Look how many arms he has. I mean, these guys too, it's ridiculous. It is amazing. And This allows these guys to send these arms through canaliculi, which lets them, number one, stay alive, but number two, exchange information. So there is a whole network of signaling going on within your bones. Crazy, right? All right. And I think just a little more of the same here. You can see these nice osteocytes. Here's an osteocyte. You can actually see its nucleus, and there's the cytoplasm chilling in a lacuna right there. And with that, guys, we are done. That was a fairly long lab, but it's a good one. There's a lot of stuff in this. Make sure you watch it as many times as need be. I gave you that little extra credit project to do. Easy way to get 2 points. And you might say, 2 points? Pfft, 2 points. But that adds up. You know, you wanna bank those little 2-point things, okay? So do that extra credit project. If you're right now, you're like, what? Extra credit project, huh? You need to go back and watch this video again. All right, on that note, I'll talk to you guys later. Bye-bye. See ya.